Section, we're going to look at solutions and mixtures, and we're going to see how do we figure out what is in that mixture. Some of this might be very remedial to you. You should know what a suspension is or a mixture. Notice that it's heterogeneous, so we're talking about two different phases. It could be like the example here, sand and water. That would be an example of a heterogeneous mixture. So obviously together they don't form one phase, one liquid phase or one solid phase or one gas phase. Now, obviously with a suspension, we're talking about macroscopic properties, so we can see the fact that it's not all one phase. That's more evidence of it being a suspension. And typically, when you're looking at suspension, you are allowing for the potential of separating by filtration. So maybe using a funnel with filter paper. Okay, so when we're looking at homogeneous mixture, and please remember, you can't assume that we're talking about liquids. It could be a solid, it could be a gas, so you got to be careful with that. Notice that they're all the same phase, and they should be uniform. So when you look at the mixture, you should not be able to tell whether or not um, they are separate components. Um, and you will see exam questions like this. If you have a homogeneous mixture, you cannot filter it. So that mixture will have to be separated using other methods. And some of those other methods are things like distillation. It could be evaporation. Notice that we could be talking about chromatography. So I don't know if you remember way back when in biology you did chromatography, you were able to separate out those different components based on their attraction with the liquid that you're using and the paper that you're using. Now, the other thing is if you were to take light, and usually it's laser light, if you were to shine a light through it, you should not be able to see anything that is being scattered. Okay, so I would know the basic terminology with mixtures. Notice that solvent, you have to be careful because sometimes you could have a super saturated solution, and typically the solvent is the one that is the largest percentage. Not always, but usually. And then the solute is the one that is the smaller percentage. So if you were to look at a combination of salt with sugar, or I'm sorry, salt with water or sugar with water, salt would be the solute, or sugar would be the solute, and water would be the solvent because the water would be the larger percentage. Now, like I said, with saturated solutions, and when we talked about the solubility product constants, so we're talking about KSP, um, we could have a saturated solution. So we have a salt that doesn't dissolve readily in water. We've seen this before. Notice that it's an equilibrium system. So you see some of the solid dissolving while some of it is re-solidifying. And with KSP, please remember we talked about sparingly soluble salts. So you were always going to have some kind of solid at the bottom of it. And all we cared about was the fact that some of the ions did dissolve in water. And you potentially will see that in an equilibrium problem. Okay, so some of the types of solutions, and I would get very familiar with intermolecular forces because that'll help you determine whether or not something will dissolve in that phase. So here is an example of water and methanol. Now, methanol is an organic compound that happens to have an OH covalent bond on the end of it, and as a result of it, it allows for hydrogen bonding. So if you were to combine the two together, you would actually get a solution because the water is attracted to the OH bond that is on the end of the molecule. So you have to pay attention to whether or not you are allowing for certain intermolecular attractions. Now, you could argue that this is miscible, and when you say that it is miscible, that means when you combine these two liquids, you don't have a layer separating them. they fully mix together, and you can't tell macroscopically that there's two different components to the solution. The other piece I would mention too is if there is an intermolecular attraction between these two compounds, you might notice that the total volume is smaller because they're brought into each other closer because of that strength of attraction. Okay, here's an example where we have a larger alcohol, and this is hexanol. So hexanol is a six-membered ring, or I'm sorry, six-membered chain. And even though it has the OH covalent bond on the end of it, it's got a large nonpolar section. So as a result of it, there is repulsion between these two substances, and we don't get a mixture. So you could say it's immiscible or not miscible. So you should see a layer between the two of them. And when you do see layers, typically the layers are determined by density. So whichever one is more dense is going to form that bottom layer. Okay, so here's an example where you have something very interesting going on. So you could have miscibility, or you could have mixing of two substances when they share similar attractions. So notice that these are both six-membered chains, and even though one of them has an OH covalent bond at the end of it, the fact that it has a six-membered chain allows for that attraction between those two substances. So you could argue that hexanol, even though it's got an OH on the end of it, it's mostly nonpolar. So as a result of it, it forms a London dispersion force of attraction with hexane. Okay, you could have an example of a solid liquid solution. Typically, we're talking about ion dipole attractions. So maybe you have salt dissolved in water. You could also have polar solids. And polar solids, an example of that would be glucose or sugar. So as a result of it, you have dipole dipole, or you have hydrogen bonding that is occurring with those compounds. Now, also, you could have nonpolar solids such as naphthalene, which is mothballs, and they would be dissolved in a nonpolar solvent. So they would have to be in a solvent that mostly contains carbon and hydrogen, and as a result of it, we have London dispersion attractions. Okay, here's an example of gas liquid solution, and I wish I could bring out my soda stream to show you this. Um, Carbon dioxide, which is a nonpolar substance, please remember the oxygen carbon double bonds, they're being pulled in opposite and equal directions, so they cancel each other out. Water is polar, but the amazing thing is, under pressure, we're actually able to get some of that carbon dioxide to dissolve, and as a result of it, we get a formation of carbonic acid. And carbonic acid is a polar molecule. It actually breaks down into ions, but it is dissolved in that solution. Also, if I wanted to, I could dissolve oxygen in water using pressure, and once again, I could have an aqueous version of oxygen. Okay, now just to argue, oh wait, I want to go back though. I just want to mention too, please remember that if you increase temperature of the liquid that the gas is being dissolved in, please remember that solubility does not increase, it decreases. So typically when you increase the temperature of a liquid and you're trying to dissolve a solid, the solubility goes up. But with gases, the opposite happens. So when you increase temperature, the solubility of a gas goes down in a liquid. Okay, so if you have a gas solution, air is a great example of it. About 80% of air is nitrogen, and then you have the smaller fractions of oxygen, carbon dioxide, vapor, water vapor. Now, we could have a situation where we actually have a gas solid solution. Now, the interesting thing is, I didn't realize this, but hydrogen gas, a way to refine it or make it pure is actually to pass it through palladium. So, palladium actually helps filter hydrogen gas so that it can only pass through a palladium metal, and this is a way to purify hydrogen gas. Now, another type of solution that we have is solid solid, and we talked about this when we were talking about metallic bonding. So, steel, which is interstitial, steel is originally iron, and iron is good at being pounded and pulled into a wire, but we sometimes need iron to be stronger and more rigid, and as a result of it, we add carbon. Carbon is small enough to fill in between the iron atoms, and it actually strengthens and makes the iron more rigid, and that's an added changed property that we desire. Now, you have to remember that if you're adding carbon to that steel, as a result of it, the density should go up. But the amazing thing is, with interstitial alloys, the actual size of the lattice is not changed very much. Okay, here's another type of alloy that we've talked about before, and it's brass. Remember, we talked about the fact that zinc atoms have a similar size to the copper atoms, and when you heat up copper that's been coated with zinc, it allows for the zinc atoms to come in and sort of pop out a copper atom, and they combine in such a way that it gives a new property to that metal. The amazing thing is, with brass, we can still pound it and we still can pull it into a wire. Notice that the density of this material is kind of an average between those two percentages. Okay, this should be review. We've talked about molarity way back when, and you should know that it's moles of solute over liters of solution. So obviously, if they give you mass, the first thing you want to do is convert it into moles. And then obviously, if you're given milliliters, you want to change it into liters. The bottom equation, we're talking about mole fraction. So mole fraction, we used it with Dalton's law of partial pressures. You could use it with expressing concentration. And notice that mole fractions should stay the same when you're talking about temperature changes, whereas molarity, we're talking about changing with temperature. Okay, so here's an example of mass and volume, and notice that you want to convert the mass to moles and the volume to liters. And please show your units in your calculations, especially using the capital M at the end with your answer. And I would pay attention to sig figs. So notice that you started with 3 sig figs for your mass, and your volume is 3 sig figs, so your answer probably should be 3 sig figs. Okay, here's a second example where we have molarity, but now they want to know volume, and they give you the moles of your original substance. So we're going in the opposite direction. We're going to use the moles and then molarity. Notice that it's the reciprocal. And they converted this to milliliters by using the conversion factor. Okay, so here they want you to describe how to prepare 100 milliliters of ammonia, and they have a concentrated solution. So don't be surprised if AP asks you to do this. It's really an important skill to have. So the first thing you would need to do is you need to figure out the amount of moles. This would be using the dilution equation. So they took the volume that they were told, and they used the target molarity to figure out the moles. And then once they have the target moles, they want to scale that up to using the concentrated molarity. And that tells you the volume of the original concentrated moles or molarity that you need to measure out. Now, this one is, I'm used to the M1V1 equals M2V2. So if you want to set it up that way, you can. But please remember that when you think about it, you're going to use more of the diluted solution to equal the concentrated smaller volume solution. And these numbers should agree with each other. So if your moles are, I'm sorry, yes, if your molarity is lower, your volume goes higher. Whereas if your molarity is higher, your volume should be smaller. And that makes sense that if we have 1.25 molarity of ammonia, we only need a smaller volume of it to equal a lower molarity, which is 1.00, and a larger volume. Now, here are the descriptions of how you would make this solution. So notice that they say you take 80 milliliters of that original concentration, you put it into a graduated cylinder, and make sure that you add enough distilled water so that the meniscus is at that mark for the total volume. Okay, here is mole fraction. I don't use this a whole lot, but this is a skill that AP would like you to have. So notice that you need to find the moles of your water, and they're using molecular weight to solve for moles. So notice that if you have 1,000 kilograms and you use molecular weight, that's the total number of moles for water. And then you want to figure out the mole fraction. So notice they originally told you 1.5, and notice that for your denominator you want to add those 2 moles up to give you the total, and then just solve for the mole fraction. Now, if you need to figure out the other mole fraction, notice that they took 1 and they subtracted it from the KOH to give them the moles of water. So together, KOH and water should equal 1.